Some of the geometrical aspects of the model. Let's see if I can recap here very quickly. We have this so-called pi plane or deviatoric plane in general. This is what we're calling the sigma 1 double prime. This is our sigma 2 double prime. And our J2 model looks like a circle when we look at it on the deviatoric plane. And this circle has a characteristic radius of kappa. Right? So we saw that my sigma 3 double prime axis is pointing out of a board. And then I very bravely attempted a three-dimensional sketch. So this is sigma 1, sigma 2, sigma 3. The key here is to get the hydrostatic axis in place. Then use a little bit of your imagination to imagine a cylinder centered at the hydrostatic axis, right? And there's a normal to your yield surface and hat, we called it, all right? And this will turn out to be df, the sigma, right? And that's where we stopped, right? So these are some of the geometrical characteristics of the model that we are defining here. So far so good? So HA, as you remember, is also known as sigma 3 double prime, right? That's what you're seeing here. So this perspective is you looking down the hydrostatic axis, right? So simple, okay? Now here are some of the ingredients of the model. So it's time to start putting them in place. So as before in 1D, you decompose the strain into an elastic and plastic part. This in additional notation is equally simple. Okay, sorry. And of course, if you have a total formulation, you can also have a rate formulation, right? One leads to the other, okay? It's more difficult to go from here to there, but definitely from direct to rate, we can go, no problem. Second ingredient, it's usually the classic definition of Hooke's law, just like in 1D, says my stress is directly proportional to my elastic strain through some elastic tangent. Okay, and we're going to say a little bit more about that. In initial notation, Ij KL, epsilon KL, E. Okay? So you can start to see some of my notation. Some fourth order tensor double contracted with a second order tensor by a semicolon that is double contraction. Last two indices contract. Okay, single contraction, say between some second order tensor and a vector, that implies Aij Vj, contraction of one index. Okay, this is contraction of two indices. Okay, so just some quick nomenclature. So from here, of course, it follows that again the rate form will follow, given that this is constant and it's the elastic modulus, call it linear. Okay, it's nothing but linear elasticity. We'll define it very clearly in a little bit. Okay, so far so good. So this is your classic Hooke's law. It's a way of computing your stress increment given some strain increment, in this particular case, the elastic strain. Third ingredient, flow, right? You need to say what defines flow. So you have your elastic, your yield surface, F of sigma and kappa, that you know it's a cylinder now in three-dimensional principal stress space. And this is defined as the L2 norm of S minus kappa has to be equal to 0, right? That defines a surface in 3D principal stress space, and that's your cylinder of radius kappa. And it's an infinite cylinder along the hydrostatic axis. We saw that it doesn't matter how much pressure we put on this thing, it's always the same, okay? Fourth ingredient, flow rule. So once we know that we're flowing, we need to define how our plastic strains evolve. Right? Epsilon dot P equals lambda dot dF this sigma. Just taking 1D, but it's three-dimensional component. But this is, as you can note, the associative flow rule. And if you want to write this in initial notation, epsilon Pij equals lambda dot, which is a scalar, dF d sigma ij. Okay, so the indices of epsilon P are the ones induced by sigma. Okay? 5, your KT or Kuhn-Tucker optimality conditions. Remember, there are 3 of them, right? The first, well, really 2, and that boils down to the third. Lambda dot equals 0, F less than 0 if the process is elastic, right? Lambda dot greater than 0, F equals 0 if the process is plastic, or if you are on the yield surface, right? That's a plastic process. And from this, you can essentially generalize that lambda dot F always 0. Right? That's your optimality condition, essentially. Always. Of course, in plasticity, you're not interested in the case when lambda dot is equal to 0 because that's elasticity, that's a trivial case, and none of these things apply. You just apply your elasticity and you're out of it. So in your code, the first thing you're always going to evaluate is, am I elastic or am I plastic? Right? That's just a yes or a no. And if you are plastic, then you know that this applies. Your F must be equal to 0. Your lambda dot must be greater than 0, and then the whole name of the game is to find lambda dot, right?
There is this case where the point is on the surface and the stays going around and around.
Right.
So lambda dot is equal to 0 and F is equal to 0 in that case.
Not sure that going around the yield surface will give you a lambda dot equal to 0.
Yeah. The point stays on the yield
Yeah.
surface, but it goes like just spins around.
Yeah, but I don't think the lambda dot is 0.
It's not?
I don't think so.
I think it is, but I don't know.
I'm not sure. I don't think so. But we can find out.
Mm-hmm.
But there is, that possibility of this thing revolving around, but I don't think lambda dot will always be 0. Yes?
Can we please explain again what you mean by this n hat here being the F less sigma?
It's just a gradient of f. I mean, I'll show it later. Right now it's just a definition. But you can show that the normal to the yield surface, the normal to f, is n hat and is defined as df dc. It's a gradient.
Okay, I guess the issue that I'm having is as defined there, n would be a second order tensor.
It is.
Okay.
Yeah, it is. In fact, it's coaxial with epsilon p dot. Right? You can see that its direction. This is essentially n hat.
Right.
Right. Yeah.
Okay. Just that so
Yeah.
far, you know, when I heard normal vector, I was used to a vector.
Right, right. But so when I mean vector, I mean in this space. So this would be the three principal directions of n hat. In the true, you know, mathematical sense, to be able to visualize it in this three-dimensional space. Okay. Good question. Yeah, so you will see me sort of going back and forth between two second-order tensors and vectors. Right? And the only way you can do that is if you speak in principal stress space. Okay. So the sixth step is to say, okay, now I need to find this lambda dot, and okay, so I'm going to use what's called the consistency condition, and remember that that was this. Okay, so right, so I'm going to evaluate f dot equals 0 because that's the one that applies. Remember, we would take the time derivative of this thing, right? So you would get lambda double dot f plus lambda dot f dot has to be equal to 0. This part is trivial, right? Because f is equal to 0 always. And therefore you're left with this. And this guy is greater than 0. So then the only possibility is for your f dot to be 0. And that's where the consistency condition came in the 1D case. In the 3D case, same thing. So now, in all models, you're always going to play with this idea of f dot equals 0 to try and find lambda dot. And I'm going to call that a plasticity complete problem in the sense that once you find lambda dot, you found everything. Okay? So let's do that. So f dot now is equal to, by the chain rule, dow f sigma double contracted with sigma dot, right, plus dow f kappa times kappa dot equals 0. Or in slow motion, in initial rotation, f dot equals df d sigma ij dot plus df d kappa dot equals 0. You still with me? Okay. Don't let the initial notation or the tensorial operations lose you. Okay. Just stop me if there's something that you can't compute. Yes or no? We're good, okay? Kappa dot is going to be equal to 0 for now, because we're going to assume perfect plasticity. Geometrically, that assumption means that my cylinder cannot expand in radius. It cannot expand or contract. It's a fixed cylinder. Okay, so my yield surface, my yield strength, if you will, remains fixed. Cannot change. All right? So I'm going to assume that, but later we'll relax that. So that means that f dot boils down to df d sigma double contracted with sigma dot. And again, and this has to be equal to 0. And again, you see this df d sigma, and if you remember my definition, this is essentially n hat. But we will give it a more formal name in a little bit. Okay, now, this is where you need to start taking things apart. df, this sigma is great, but my f is not really in terms of sigma, isn't it? It's in terms of s, and not only s, but the L2 norm of s. So what I really want to compute is this. That's really what I mean, right? That's the one term I want to evaluate with respect to sigma. Okay, and this is the part that scares people away from plasticity because it's a lot about this tensorial algebra and taking this derivatives, you know, by hand analytically. Okay, so use again your chain rule. This is really this, isn't it? You want the derivative of a L2 norm of a tensor with respect to itself, and then you have to multiply that with respect to what you really want. In initial notation, I won't do this all the time for you guys, but I think at the beginning it's useful. This means this. Okay. So this is a classic derivative, which is the derivative of a deviatoric portion of a tensor with respect to itself, right? And this is also a classic derivative, which is the derivative of the L2 norm of a second-order tensor, symmetric second-order tensor with respect to itself. So they're both going to be pretty useful to you in general. So let's do the first one. So L2 norm of any tensor is Sij, let's say, Sij 1/2. Right? So I really want d of L2 norm of S dskl, that is d dskl of Sij to the 1/2. Right? And then I just plow away. This is equal to the 1/2 comes down, right? The stuff in parentheses remains the same, now with a minus 1/2 in the exponent, right? And then I take the thing inside. So I need to do d dskl of Sij, okay? And I'm done. So evaluate these. Let's do it over here. So dsij, Sij with respect to dskl equals, if you take the first guy, dsij, dskl, and sorry, this will be multiplied by Sij, plus another guy that will be Sij, dsij, dskl. So there, you can start to see they're identical. Okay, they're going to be the same thing. So what is dsij with respect to dskl? Can you tell me? Have you ever learned in continuum mechanics what that is? Right. Delta, so let's say delta ik, delta jl, right? That's right, but almost. You have to add a one. Well, I think it's important later on when you code this thing to keep it formally as these plus delta jk delta il. And the reason why that's going to be important is that this is a second order tensor that is symmetric. So when you take the fact that Sij equals 1/2 Sij plus Sji. Then you get this formal result, and that will be important when you do the void notation of all these things and you put in a fundamental code. If you just leave the formal correct part, which is delta Ik, delta Jl, you will lose this symmetry component, okay, the symmetry property. So this is what people call the fourth order symmetric identity tensor, okay? Because when you hit a tensor with that, you will get its symmetric part, not the full tensor, but just its symmetric part. See what I mean? So you gotta be a little careful with that. As long as everything is symmetric, there's no problem. But then once you start to put this in void notation, this 1/2 will create issues for you if you're not careful. Okay, so I think we agree that, okay, all we get from this then is what? What do you get from this whole thing?
Sij times all that, all the 1/2.
Right, but so when you hit Sij with this, you just get Sij back. The same from here, right? So you're just gonna get 2 Sij from this whole thing. You see that? I'm sorry, but the indices are wrong. It's SKL, right? Good. Yeah, pay attention to the indices. Everybody on board? Okay, so the formal derivative of that is twice Sij. So you can see that this 2 multiplies that 2, and you get from this whole thing, from del SKL, you get SKL over Sij to the 1/2, or in direct tensor notation, this is the derivative of the L2 norm of a second order tensor that is symmetric is equal to the tensor itself over its norm. Okay? And this we're going to formally call n-hat. Okay? It's a unit tensor. So let's write some of the properties of n-hat. I can erase this now, right? Everybody got this. So n-hat is a unit tensor. Meaning that its L2 norm, right, is equal to 1. Because it's S divided by its magnitude, its L2 norm, right? So when you take the L2 norm of that, you get 1. It's got another property. What's the other property it's got? What kind of a tensor is n-hat? It inherits a property. It's symmetric, yes. What else?
Trace is 0.
Right, it's traceless. So n-hat is symmetric, but it's also deviatoric. When you contract it with the identity, in other words, when you take its trace, you get absolutely 0. So n-hat is deviatoric. Okay, so it's got no business with the hydrostatic axis. Makes sense from our picture again. This thing is the normal to the cylinder. In other words, this guy lives radial away from the origin, right? And away from the hydrostatic axis. So far, so good? Okay. What else do I have? Okay, you guys are killing it. All right, so, okay, but let's see, so we evaluated, so we really started this whole thing. That's when you know that what you're doing is complicated, because you even forget why you were computing this. Okay, so what you really wanted was df this sigma, right? And you just got this part, right? We just realized that this is n hat KL, given our current nomenclature, right? Now we need this other part, right? We need to know what the derivative of S with respect to sigma is. Okay, so now we're gonna go get that. So let's do that here. Okay, so these ds, again, classic derivative, for the simple reason that it's classic. And okay, I'm going to leave the indices flipped just to be evil, because it doesn't really matter. Okay, you should be able to play with indices. So I'm just going to take the derivative of the deviatoric part of a tensor with respect to the tensor. So, okay, remember that S is the deviatoric part of sigma, so it's sigma minus its volumetric part, right? Which is let's use another, let's call this MM. Is that right? Right? This whole thing, it's Sij, right? So it takes sigma, and then it subtracts its volumetric part, which is 1/3 sigma mm. Is that right? Let me see. If I'm making a mistake. Yeah, I think that's right, because I have it here as P. Yeah, so we've baptized this guy as P. So, okay, so if you want to write it in more compact way, this is sigma ij minus P delta ij. Okay?
But P depends on sigma as well.
Pardon me?
P depends on
Yeah.
sigma.
Yeah, it's a trace, essentially, right? So, okay, so the first one you already know. We just went through this painful process of taking the derivative of a second order symmetric tensor with respect to itself. What is that? Should just come up. What is it? It's essentially this identity, right? This fourth order identity tensor, right? The symmetric projection, the symmetric identity. So this would be, in our nomenclature, this guy, which if you want to expand, just so that you recall, is 1/2 delta ij delta KL plus delta, is that right? No. This is I, K, good, thank you. J, L, and then this guy is J, K, delta I, L. Right. Okay? So that's a classic result. And then all we need to do is find out what dp this sigma ij is, or in this case KL. Delta ij will be done. Yes? So we look at here. So P is nothing but 1/3 of this guy, so dP d sigma KL is nothing but 1/3 d sigma MM d sigma KL. Okay? And applying the same rationale, the same results that we know from before, this is 1/3, right? Delta M K delta M L. The dummy indices contract. And this is 1/3 delta KL. Plug it back in. So dsij d sigma KL is nothing but my fourth order identity tensor that extracts the symmetric part of any tensor minus this guy, right? 1/3 delta KL delta IJ. In direct notation, this will be ds d sigma equals the fourth order identity tensor minus 1/3 delta dyadic product delta. This is the dyadic product. That just means that you have two second order tensors. They have no indices in common. They must be taking the juxtaposition or the dyadic. Okay? So then we go back and say df d sigma equals dl2 norm of s ds double contracted with ds d sigma. We discovered that the first term is n hat. We discovered that the second term is this guy. Come on. And then we go through the operation. N hat double contracted with a fourth order identity tensor. What do you think you get back? Huh? N hat. Okay, that's the problem. Never forget that. That's the property of identity. Okay, you get whatever you hit it with, you get that same thing back. Okay, double contraction of any second order tensor with I will give you that tensor back. It's symmetric part. But since n hat is symmetric, you just get n hat back. Okay, so the first term yields n hat. The second term, n hat double contracted with the identity, with one of the identities. What would that give?
Self also.
No. Trace of n hat. What's a trace of n hat? 0, because n hat is deviatory. So from this whole thing, you convince yourself of this property that I put on the board way back then, that df is sigma is n hat. So let's do it in slow motion, in initial notation, so that you can appreciate the details just this one time, and then you'll have to do it on your own later. Okay? So, I have the following operation. N hat double contracted. The order of contraction and all that matters. So pay attention. 1/3. Okay, in initial notation, this means n hat, let's say, ij, double contracted with fourth order identity tensor ij kl minus 1/3 delta ij delta kl. Then you can expand this guy into what it is, right? Okay, so start with the first one. You take n hat ij, and it will contract with these guys here. The first delta will replace the I with a K, right? The second delta will replace the J with an L. So from that first contraction, you will get n hat K L. N hat ij with these guys. The first delta will replace the J with a K, and the second delta will replace the I with an L. So you will get N hat L K. But since N is symmetric, you just get N hat KL back. Okay? Then, in the second term, you get N hat IJ double contracted with this guy. So the I gets replaced by the J, or the J gets replaced by the I. This becomes N hat II, which is a trace of N hat, which is 0 because N hat is deviatory. Okay? So you convince yourself of this result. Okay? The ability to go back and forth between indicial notation and direct notation is crucial for a person working in computational mechanics. Okay? Your tensor manipulation, your indicial manipulation, your comfort with going back and forth will make your life, even coding, a lot easier. Okay? Most of the coding mistakes I see actually are born here. Someone computes something by hand because they made a mistake in the indicial notation or in the direct notation, and then that goes into their code, and it's over. An error here will corrupt everything. So be very, very good. Okay. So we're here. This puts us in a position to define what I will many times refer to as the deviatoric projection. Is this fourth order tensor that when you double contract a second order tensor with it, guess what it gives you back? The deviatoric projection, or the deviatoric component of that same tensor. So if you were to hit sigma with this guy, what do you think you get out? S. Okay. Why? Because when sigma hits this guy, you get sigma back. And then when sigma hits the second component, it hits one of the dyads, right? And that essentially executes the trace, right? And 1/3 times the trace times the identity, that's the volumetric component of sigma, gets subtracted from sigma. That is, by definition, the deviatoric part of sigma. Okay, so and then you do it with any tensor, and that's exactly what you do. Okay. So that leads us to the definition of also the volumetric projection, which is, guess what it's going to be? Just, did I? Did I include the 1/3? Maybe it didn't. Yeah, let's leave it out. Okay, so that would be this guy. So there you have it. So essentially, your deviatoric projection is your fourth order identity minus 1/3 of your volumetric projection. You can imagine what this guy does. You hit any second order tensor with this guy, and you essentially get the trace of that tensor, which gives you the volumetric part. So again, if you hit any second order tensor with a volumetric projection, say sigma, you will get trace of sigma times z. Okay, which is essentially the volumetric component of sigma. I forget if I include the 1/3 or not. Okay? So, I think what you need to do now is come to terms with all the tensor manipulation, all the additional notation, direct notation, make sure that you can go back and forth, make sure that every derivative makes sense too. Yes, sir.
For dft sigma is equal to n hat, that's assuming that k prime is equal to 0. So if k prime is something else, you have to go through the whole entire derivation again.
No.
No?
No. No, because remember that we got this df, this sigma, so remember that there are two terms in f. There's sigma and there's kappa. And this term came from df, d sigma, sigma dot, and then there is df, d kappa, kappa dot. So what we just found out is that this guy is n hat. So that will remain true even if this is non-zero. Yeah. So in that case, you would get n hat double contracted with sigma dot plus df, d kappa, whatever that is, kappa dot equal to 0. Right? In our case, this happens to be 0. So in fact, that's a great segue into reevaluating again what we started looking for, which is our f dot, our consistency condition, which is d sigma, df d sigma double contracted with sigma dot. Now we know, right, that this is n hat double contracted with sigma dot, and that has to be equal to 0. Again, in the case when kappa dot equals 0, so in the perfect plasticity case. So what does that mean? Again, make an analogy with vectors. What does it mean for n hat double contracted with sigma dot equals 0? If these were vectors and they would be orthogonal, right? This would be an orthogonality condition. So if you go back to your principal stress space and you see n hat as a tensor, as a vector, right? That gives you a sense for the possibilities for sigma dot. What your consistency condition is telling you is that sigma dot needs to always be orthogonal to n hat, right? So that means that you can only allow for increments in stress that are on the surface or along the surface of the cylinder, right? All of your sigma dots need to be tangent to the cylinder. They cannot have any component in the direction normal to the cylinder. Okay, so in the case of perfect plasticity, meaning that your radius cannot expand or contract, your pore sigma is limited to living in an infinite cylinder, right? And it's limited to only taking new values along the surface of that cylinder. But it can never go outside. It can come back in and become elastic again, but if it wants to continue to be plastic, its only potential increments are tangent to the cylinder. Okay? Remember that. So, the tangent to cylinder. Again, imperfect plasticity. If I get a little bit ahead of myself and I enable my radius to change, that condition will be softened, right? I will enable sigma dots to go up. So far, so good. Okay? So my consistency condition, that's why it's called consistency. It puts some constraints that make your formulation consistent with whatever ingredients of plasticity you have. Your plasticity ingredients say that F has to be equal to 0 during plasticity. Then you enforce that further by saying, therefore, F dot has to be equal to 0. And then you have come up with a condition that enables or is consistent with the fact that F dot has to be equal to 0, meaning that sigma dot has to be tangent, or in other words, orthogonal to n hat. You violate these and you will violate your ingredients of plasticity. For instance, if you have a sigma dot that is not orthogonal to n hat, you will enable it to take values that are outside of a cylinder. Not possible. Okay? So that's inconsistent with your formulation. Therefore, your consistency condition is your police. It's the one that makes you follow the rules, right? That you yourself came up in the model. Okay, now if we go back to our other ingredients, let's go back to Hooke's law. We play exactly the same game we played in 1D. And we say sigma dot equals CE epsilon dot E. And then you say, okay, by the additive decomposition of the strains, this becomes epsilon dot minus epsilon dot P. And then by the flow rule, this becomes epsilon dot minus lambda dot df d sigma. And then by the properties of F, I already know what df d sigma is. What is it? What is it, guys? N hat, right? Great. So sigma dot starts to take a very prescribed form that is again a result of your formulation. It's no accident. It follows the structure of your ingredients. Okay? And again, recall what we are after. We are after the value of lambda dot. That's what we started to look at the consistency condition to go into, to arrive at this, what we call the plasticity complete problem, to solve the whole thing. Right? Then so we armed with this, we go back to the consistency condition that says n hat double contracted with sigma dot has to be equal to 0. Right? This is my consistency condition. And I'm going to put it together with this definition of sigma that is consistent with Hooke's law with flow rule and with the geometry of my yield surface, and I'm going to find lambda dot. So I'm going to do that here. So n hat double contracted with sigma dot equals n hat double contracted with CE double contracted with epsilon dot minus lambda dot n hat, correct? And my consistency condition requires that that's equal to the scalar 0. So far, so good. So I get then that n hat double contracted with CE double contracted with epsilon dot minus n hat double contracted with CE double contracted with n hat times lambda dot have to be equal to 0. You're comfortable? Note that these are all scalars. The first one and the second one, right? Because they are second order tensors double contracting with a fourth order tensor at the front and at the back. That is a scalar product. Okay? Let's do it in conditional notation. N hat CE epsilon dot, and there are two double contractions. This means Nij CEij KL epsilon dot KL. This yields a scalar. Okay, it's a scalar product. Therefore, since it's a scalar product, I can do regular algebra, and I get that lambda dot will always be equal to 1 over whatever n hat double contracted with CE double contracted with n hat is times, well, actually, there's no need to further complicate things. You see that? Some simple scalar. And that's not 0, Alex. Even though we're traversing along the pipe, the cylinder, that lambda dot is not 0. It won't be. Okay, so now it remains to define what this CE is, right? So the CE is your linear elastic fourth order tensor. And all of you have seen it in one way or the other. So, of course, I always abuse my notation, so I have here the bulk modulus as kappa. Let's call it kappa wiggle. For lack of a better name, 1 diet 1 plus 2 mu fourth order identity tensor minus 1/3. Another way you see it defined is kappa wiggle the volumetric projection plus 2 mu times the deviatoric projection. That's a much more compact. It's your classic fourth order linear elastic tangent. most of you maybe have seen it in the following way. When people write sigma ij equals C E I J K L epsilon E K L. Take this product, contract epsilon with these guys and see what you get. So let's see what we get. So we're going to get kappa wiggle, the bulk modulus, right? And then epsilon KL is going to hit one of these guys. It's going to double contract, actually the second guy, because it's hitting from the back. So it's going to hit this guy, so it's going to get the trace of epsilon KL. So you're going to get epsilon, let's say, MM dot. And then the identity is just going to come along for the right, delta ij. Then epsilon can hit this guy, right? And we know what happens when we hit a second order tensor with the deviatoric projection. We get the deviatoric part of that back, right? So let's do it slowly. So we're going to get epsilon ij dot minus, right, this guy again, 1/3 epsilon m dot e, right? Right, so this is the deviatoric component of epsilon ij e dot. Sometimes people give it a symbol. They call this e ij e dot. That's it. Right, so the usual way in which you see this relationship is in the, what I would call the expanded version, where you see in textbooks, especially in elasticity textbooks, this is how you see it. But you also see it in another version. If you free this guy, let this guy free, right? You're going to get, and then you collect the volumetric terms and let this guy out. You're going to get something that looks like kappa wiggle, right, minus 2/3 mu, right? Epsilon m dot e delta ij, and then you're just going to get 2 mu epsilon ij e dot. Does this look familiar to you? This? No, maybe? What do people usually call this guy?
Bulk modulus?
Huh?
The bulk modulus?
Kappa wiggle is the bulk modulus. Yeah, so people usually call it lambda, also known as Lamé constants, right? So there's this Lamé constants, lambda and mu, that you usually see in elasticity textbooks. That's, so if you were to call this, again, I'm using notation, it's called a lambda wiggle. So these two guys are usually called Lamé constants. So you typically say sigma ij dot equals lambda wiggle, the volumetric part of the strain rate plus this 2 mu, the full strain rate. Okay? I just wanted to go through this in additional notation so you feel comfortable with with the notation we're adopting. If we were to write it like this, now, let's go back to full notation. I need your help. Let's write this one. Sigma dot equals what? Let's write
Which one are you writing?
this one.
The trace of epsilon by b.
Right, but I want, so I'm gonna have at the end,
Um,
this guy, right? I always wanna put some modulus in the middle.
Stated.
Not quite. You need something similar to that identity.
Yeah, okay, times the name.
Right, which is what?
E.
It's a volumetric projection. See that? Which is I, this guy is delta diet delta, as Alex is pointing out. Right, so when you hit this with this, it will give you the trace of these, and then one of the deltas will survive. Okay, then the 2 mu comes along for the right times what? Fourth order identity. Okay, then I can continue writing this in the other form and say, according to this form that we have here, then that becomes kappa wiggle, again the volumetric projection, plus 2 mu times what? In this form. The deviatoric projection. Are we okay? We're on the same page? Any of these guys, actually all of these guys, are your CD. Okay? All they're doing is hitting your elastic strain rate, and as a result of that, they're giving you your stress increment. Okay? There are just many different forms of writing the same thing. Are we happy? Sort of? Okay. Let's keep the fun rolling. So let's go back here to do this n hat double contracted with CE, because that's what we're after. So let's do a pop quiz now. Let's take this version. You want to know what this is. All right, so this is n hat double contracted with what we're calling kappa wiggle, which is the bulk modulus that we just defined. Before I forget, this is the shear modulus. Before I forget, so it's easier to see it here. So the bulk modulus, as it turns out, is the one that will control your pressure. Remember that every second order symmetric tensor can be decomposed into a volumetric part and deviatoric part. You're seeing them. You're seeing where they come from. The first one comes from the volumetric part of the strain, the elastic strain. And the second one comes from the deviatoric part of the elastic strain. Okay? Bulk modulus, what does it control? It controls how much your pressure increases or your volumetric part of your stress increases due to volumetric increases in strain. Shear modulus controls how much your deviatoric part, your S part of sigma, increases due to an increment in the deviatoric part of the elasticity strain. And elasticity assumes that those two processes are independent of each other. Meaning an increase in shear strain yields no increase in volumetric stress. In plasticity, that's in general not true. You can have processes in plasticity that are what's called associated with each other, right? They're coupled. You can have a shearing deformation that induces an increase in pressure, something that in linear elasticity you can never get. So I just wanted to point that out because I think that's important. Okay? So keep an eye on this. Okay, back here. So your N hat double contracted with kappa, volumetric projection plus 2 mu deviatoric projection. What is this equal to? What's the first term equal to? By now, you should do this on your sleep. You should be at least having dreams about these contractions tonight. What's N hat double contracted with PV, volumetric projection? It's a big fat zero, right? Because the volumetric projection, by definition, takes the trace of N hat, that's zero, so that disappears. N hat double contracted with PD, with the deviatoric projection, what is that? N hat, right? So this whole thing, even though it looks scary, it's nothing but 2 mu N hat. Okay? It looks daunting when you look at it the first time, but it's very simple. All right, so my entire numerator has been resolved. What is my denominator? Given this result. 2 mu, right? So lambda dot equals 2 mu N hat double contracted with epsilon dot. All of that over 2 mu. 2 mu and 2 mu go away. And lambda dot equals N hat double contracted with epsilon. So, interesting. So, recall that epsilon dot P equals lambda dot N hat. And this, by definition, is a unit vector or unit tensor, where the magnitude is given by lambda dot, right? That's the strength of my plastic strain increment. So what this is saying is that my plastic strain increment is proportional to my total strain increment. 0 total strain increment, 0 plastic strain increment. That's when you get a 0 in lambda dot. Otherwise, N hat takes the projection of epsilon dot. The projection where? Along the radial direction of a cylinder. Right? N hat or epsilon dot can be in any direction in general. You can impose any strain rate. The plastic strain rate says, wait a minute, I appreciate that you have your values in any direction. I'm not concerned about just any direction. The only direction I care about is the one that projects onto the N hat direction. So if epsilon dot is here, vertical, N hat is taking that projection And here, it's gonna give you, this will be epsilon dot p. Right? This would be the magnitude, and n hat will be giving you the direction. And in fact, guess what? This will be epsilon dot p, epsilon dot e. Right? And in fact, therefore, if that's true, this will be the direction of sigma dot. See that? You have a strain increment that does whatever the hell it wants. There's no restriction in epsilon dot. Then your plasticity says, wait a minute, you can't just do whatever you want. You have to be consistent. Epsilon dot will get a projection onto n hat, and that will give me the strength, the scalar value, the measure of plasticity. And then my plastic strain rate will be in the direction of n hat. Then, by the additive decomposition, you know that you have no other choice but for the other component to be the epsilon dot e component, right? So that when you add epsilon dot e plus epsilon dot p, you get epsilon dot. Okay, that's your additive decomposition. Epsilon dot e induces your sigma dot. Sigma dot is collinear with epsilon dot e. We proved it here. So whichever direction epsilon dot e is pointing to is the direction that sigma dot is pointing to. And all of that is consistent with every single one of the ingredients that you have laid out. And it has a very vivid geometric interpretation. And that's the beauty of plasticity, that you go back to some piece of sheet, some sheet of paper or some blackboard, and you see it, okay? It's there. So, as opposed to other theories, for instance, that are very popular, mostly in Europe, hypoplasticity, for instance, has been very popular because of its mathematical simplicity and elegance. It doesn't lend itself very nicely to the geometric interpretations that plasticity, on the other hand, does. Questions about these? Please, this is your moment to ask questions, because this is where the concepts are being laid out. When would you get lambda dot equals 0? There is one case, one special case. What's the condition? So the trivial one is epsilon dot equals 0. Okay, fine.
The orthogonal.
Right. When epsilon dot is tangent to the cylinder, then you will get a perfectly orthogonal strain increment. And let's see if we can figure that out. So for instance, if epsilon dot is what? Can you think of a physical strain increment that will always be orthogonal to n hat?
Hydrostatic.
Volumetric or isotropic, right? So if you happen to be here, you were on the yield surface, you were at plasticity, and then all of a sudden your subsequent strain increments are nothing but volumetric, then your plasticity will say your lambda dot will be 0. That's a special case.
And F is 0.
And F will be 0. Then and only then, in that non-trivial case, you will get this condition with lambda dot, you see. Okay, let's close the loop by saying, well, we're a few lines away. So if we come back to this, given that there doesn't seem to be any questions, we put this thing together. This is a scalar. All I'm doing is going back to the flow rule, introducing this result we got. And then I'm going to do some rearrangement and write this as n hat diet n hat double contracted with epsilon dot. It's the same expression, and the way you can convince yourself is to go back to initial notation. So this is sigma n hat, let's say ij. This is epsilon ij because they're double contracting. And let's say this is nkf. Wait, no, something. There's no double contraction there. I'm sorry. There's no double contraction. This is just a scalar, which is lambda dot times this two second order tensor. Okay, so you have the double contraction here. This just has free indices. So then you rearrange things. N hat, you put it together with n hat. So that means this n hat is this first n hat. And then this n hat is the second one. How do I know that? How do I know which one's which? How do I know that this one has to be the last one?
Using index notation.
Because that's the one that's contracting with epsilon dot, okay, and the order matters, okay? So this is a fourth order tensor. And now leaves me ready to put everything together in one final step, right? Because I go back to Hooke's law that says sigma dot equals CE double contracted with epsilon dot E minus, I'm sorry, this is epsilon dot, minus epsilon dot P CE double contracted with epsilon dot minus, I'm just going to introduce this, n hat diet n hat, all of that, double contracted. What am I doing? I'm okay, right? Yeah. Yeah, it's okay. Yes. It's all right. It's all right. It's okay, huh? Okay. And then, okay. And then I use the fact to pull everything together. I use the fact that this, I know what this contraction of CE with n hat is already, right? What was it? It was a 2 mu here. N hat double contracted with CE is 2 mu n hat. Okay, so CE double contracted with epsilon dot minus 2 mu n hat diet n hat double contracted with epsilon dot. Okay, now you can put everything together. Say, okay, sigma dot is equal to CE minus 2 mu n hat diet n hat, all of these double contracted with epsilon dot. And guess how we call this guy in parentheses? This guy has a classic name of CEP, or the elastoplastic tangent operator. It operates on the total strain rate to give you the stress rate, just like the Hooke's law, just like the linear elastic one. But it has the added advantage that it takes into account the plasticity. Okay? Many people like to write this thing in Macaulay brackets, meaning that this only gets activated if you have plasticity. So, in other words, if lambda dot is not equal to 0, then you activate this corrector. Otherwise, you just leave this. Okay. But, okay, that's a formality. So this is the elastoplastic tangent operator. Okay, I'm going to stop there and essentially say that you can start to see where the algorithms came from as well, because you can start to see that there's a portion that is elastic and then it gets corrected, right, or fixed given your plasticity constraints. All right, so the process, let's say the trial part of the algorithm can always start by assuming that this is 0, for instance, and taking the first approximation, right, by making the first increment just elastic, and then finding out if that doesn't violate any of your ingredients, let's say consistency. And then if one of those is violated, then it comes back and it corrects. Okay, but you can start to see this very nice structure that is almost additive, okay, where you have something that looks like very elastic and then you fix it or correct it with something else. Okay, so I think that we are getting to the heart of the plasticity concepts in 3D. And I think that if you compare with 1D, there's essentially no difference. The only difference is that now instead of speaking of only scalars, now we're speaking of tensors, second-order tensors, fourth-order tensors, vectors, principal stress spaces. Okay, the concept, the problem gets geometrically more complex, but the concepts are the same. Okay, you keep playing with the same concepts. And then once you digest this model, which is a simple model, the radial model, then the other models will essentially build on complexity. For instance, the next level of complexity is letting your radius expand or contract. The next level of complexity after that will be letting your cylinder float away from the hydrostatic axis. Right? The next level of complexity will be forgetting about the cylinder and putting some more complex surfaces, and so on and so forth. But the principles are the same. F equals 0 all the time. Lambda dot needs to be consistent with your formulation. Hooke's law remains the same. Everything remains, the machinery remains the same. The geometry changes. Okay? And the geometry is dictated by this form of F and by the rules that you enable F to evolve by. And that's it. Every model is just a variant of that. Any questions?
I think that it is important to point out that the CEP only works with plasticity. So I've seen a lot of people coding it from the beginning and computing the CEP from elasticity, and then they go like, Drucker-Prager doesn't converge for the first time.
Right.
It's an exceptional case. I found it.
Yeah.
And the mistake is in computing the CEP.
Yeah. So that's why it's important to remember that this second part is only there. That's why the Macaulay brackets. So they're only true, they're only present when lambda dot is not 0. If you're in an elastic step, this guy gets dropped out, and then everything is just given by you. Good point. All right, guys, we'll see you next time.